Welcome. We are learning the chain rule today. So this is chapter 3.6 in our AP textbook. If you are following along in our notes packet, we are on page 4 of our notes packet. And our goal today is to derive the chain rule and use it to differentiate functions. I'm actually, just to save us some time, I'm going to skip over some of what's in this box here. This is an activity we would have done in class together. And I want to take a look at examples number 3a and 4a. And we're going to find our derivative of y the way that we know how to do that right now, which is to start with a rewrite. So I would expand this out. So we would have 25x squared minus 15x minus 15x, so minus 30x plus 9. And then I find my derivative using my power rule, so we would have 50x minus 30. So what I want to explore today is, can I, instead of expanding with a rewrite first and then differentiating, can I just apply my power rule right now? Can I just pull my 2 out to the front, bring down that 5x minus 3, and drop the power down to a 1? If I did that, so I'm just kind of experimenting here, if I did that, I'd be left with 10x minus 6. And it's sort of close to the example that we know is correct, but I'm off by a multiplier of 5. That's curious. So if I took this and multiplied by 5, then I would actually have 50x minus 30, which is my true derivative. Let's try this with a different function. So I've taken one very similar to number 3, but we've got a squared in there. So we're going to differentiate our traditional way, which is with a rewrite first. So 5x squared times 5x squared would be 25x to the 4th, minus 15x squared minus 15x squared, that's minus 30x squared, plus 9, and then we'll take our derivative using our power rule. So 4 times 25 is 100x cubed minus 60x. So what if we tried to just apply the power rule and pull my 2 out to the front? And if I distribute that, that would give me 10x squared minus 6. This time around, I'm off by what looks like a multiplier of 10 and also a multiplier of x. But if I had multiplied this by 10x, I would have the actual true derivative, which is 100x cubed minus 60x. So you might be thinking, why are we looking for a new rule when we have one that works perfectly fine? Well, what if the power was not 5x minus 3 squared? What if it was 5x minus 3 to the 12th power? I don't know about you, but I do not want to expand out that 12th power out to 13 terms. So it is going to be very helpful for us to have an alternate way to work problems that are representing a binomial squared or any expression raised to a power. So if you look at this multiplier that we're missing, here we were missing a 5, here we were missing a 10x. Where is that 5 coming from? Where is that 10x coming from? Well, it turns out that it's coming from something having to do with the binomial that is getting raised to that power. And you'll notice that the derivative of that inside expression, 5x minus 3, is 5. And the derivative of that inside expression, 5x squared minus 3, is 10x. So this chain rule allows us to avoid rewrites and differentiate something that is written in the form of an expression or a function within another function, a function raised to a power, for example. And I can apply my power rule by pulling my 2 out to the front, but what I'm missing is that I had to multiply by the derivative of that inside function. So the chain rule technically looks like this. we are taking the derivative with respect to x of f of g of x. So it is a composite function, a function within a function. If you're wondering what a function within a function looks like, the most common three scenarios that we'll see right now would be some kind of expression raised to a power. That's the example that we looked at in number 3 and number 4. Some kind of expression inside a radical, which we know is the same as that expression raised to the 1 over n power, which means it really is the same type of scenario as an expression raised to a power, and a trig expression with an expression within it. So a trig function with something other than x or theta or y in here. There will be a couple more applications where we will apply the chain rule when we learn how to differentiate natural logarithms and e to the x, which is coming up very soon. So what does our chain rule look like? Well, we start with the derivative of the outer portion. The outer portion is my f. So the derivative of f would be f prime, but I leave the inside part the same. We only differentiate the outside part. And then I multiply by the derivative of the inside part. So the derivative of the g of x would be g prime of x. So our chain rule is f prime of g of x times g prime of x. All right, let's take a look at some examples. So on the next page, number 5, we have a binomial raised to a power. So what we're going to do, we're going straight to the derivative. And we're going to pull our power out to the front. Let me see if I can focus this a little bit better here. That's much better. So we're going to pull our 3 out to the front. Our 2x plus 8 carries down. And then our power drops down to a 2. But now I'm going to multiply by the derivative of the inside function. The derivative of 2x plus 8 is 2. And so my one final step will actually just be to clean this up and multiply the 3 times the 2. Everything else we will leave as it is. We've got another example, number 6, which is in kind of a similar setup. We're going to pull our 8 out to the front times 6x squared plus 5. Drop our power down to a 7, and then we are going to multiply by the derivative of the inner part, the inner function, which would be 12x. So our last step is just to clean up and combine anything that we can. 8 times 12 is going to give us 96x times 6x squared plus 5 to the 7th power. Okay, so take a look at 7 and 8. These are perfect examples where even if we wanted to expand out something like number 6, which we don't have that option on 7 and 8. So when we take the cosine derivative, we're left with negative sign. But we've only seen examples up until now where the angle is a single variable. Well, what if it's an expression? So my inner function is the 3x minus 5. My outer function is the cosine. So when I find my derivative, I'm going to start with the derivative of the outer function. So the derivative of cosine is sine. Your angle stays the same, just like the inner part here when we dropped our power stayed the same. But now we multiply by the derivative of the inner part. So derivative of 3x minus 5 is 3. And just out of habit, I usually like to bring my numeric coefficients out to the front. Take a look at example like number 8. So on number 8, first thing, a coefficient can just carry down, just like it always does. The derivative of secant x is secant x tangent x. So the important thing is that the angle stays the same when we take the derivative of secant. So the derivative of, so my outer function is the secant, my inner function is the 3x to the 4th. So the derivative of secant is secant x tangent x, and the angle remains the same, 3x to the 4th, 3x to the 4th. But now I multiply by the derivative of the inner portion, which is the the derivative of 3x to the 4th, which is 12x cubed. Let's fix that. 12x cubed. So the last thing that we can do is combine the 12x cubed with the 7 all the way out in the front. So that would give us 84x cubed secant of 3x to the 4th tangent of 3x to the 4th. Remember, you can't combine this 3x to the 4th with anything. That is an angle, and it's attached to our secant. All right, take a look at number 9. So I prefer to differentiate looking at radicals in a rational exponent form. That way I can apply my power rule. So the first thing I'm going to do is I am going to rewrite this so that my square root is represented as a 1/2 power. And now I'm finding my derivative. So now I use my y prime notation. My 1/2 comes out to the front. 7x minus 4, the inner part stays the same and carries down. My power is going to drop down from 1/2 minus 1 would be negative 1/2. Now, when you are rewriting this, we're going to follow the same rules that we followed back in the power rule section, which is I want my final answers to have positive exponents and radicals. So this whole expression is going to push into the denominator. So I'm going to start with my 1/2. And this 7x minus 4 pushes into the denominator, and it's raised to the positive 1/2 power, but we know a 1/2 is the same as a square root. And that would be the simplest form of our final answer, where the exponent is written as both positive and we're using radicals instead of rational exponents. All right, take a look at example number 10. You may have remembered that we did an example like this in the trig section, where we rewrote this as sine x times sine x, and we used the product rule. That is absolutely an option here. But what if you had sine to the 5th power? That might be a little bit more work. So I'm going to practice this with the chain rule, and I do find it very helpful when you are working with a trig expression raised to a power to write the power on the outside, because it can be tricky to determine what is your inner function and what is your outer function. I'm just realizing on the last problem, we were so caught up in that rational exponent, we forgot to apply our chain rule. Let's go back and fix that. So our derivative of our inside function, I should have known because I forgot to underline my inner function. My inner function was the 7x minus 4. So when we took our derivative right here, the derivative was a 7. And so in your numerator, we actually have 7 over 2 here. There we go. Okay, let's go back to number 10. So we're going to apply our power rule here. So this is y prime, and my outer function is the squared expression. My inner function is the sine x, and it is very easy to accidentally reverse that order. So rewriting it in this form of the trig expression to a power makes it a little bit easier to see which one's the inner function, which one's the outer function. So I start with the derivative of the outer function, which means my 2 comes out to the front. The inner part stays the same. My power drops down to a 1. Then we multiply by the derivative of sine, which is cosine. And I am absolutely okay with what you have here for a final answer. But if you're working out of your AP textbook, which tonight, it depends on what kind of homework I assign, but if you're working out of your AP textbook, they might recognize that 2 sine x cosine x is the same thing as the sine double angle formula. So they might write it like this. Either one of these is okay for me for a test. If you are an IB student, either one of these are okay, and IB will let you know if they want it in a different format. All right, take a look at number 11. I've got another trig expression raised to a power, so I am going to rewrite this. So we have tangent of 3x minus 1, but this whole thing is being raised to the 2nd power. Whoa! What do we have here? We have an innermost function, the 3x minus 1. We have a middle function, which is the tangent, and then we have the outermost function, which is the squared. So this is actually a function within a function within a function. So instead of differentiating f of g of x, this is like differentiating f of g of h of x. So we still start with the outermost portion. So my squared. So that's a power rule. So my 2 comes out to the front, and everything in here stays exactly the same. My power drops down to a 1. times the derivative of the middle function. So the derivative of tangent is secant squared. The inner part stays the same, so your angle stays the same, times the derivative of the innermost part, which is the 3x minus 1, and that derivative is 3. So what can we do to clean this up? Not a whole lot. All we can do is combine the 3 and the 2 together to get 6 tangent of 3x minus 1 times secant squared of 3x minus 1. Okay, take a look at example number 12. So I've got now this has a function within a function. We have x plus 1 within a cubed, and we have x squared minus 5 within a fourth power. But the bigger picture is that we actually have a product rule. So we have an expression times an expression, which means I'm actually going to start this one with a product rule. And then when you do your product rule, we take the first function times the derivative of the second. When we take the derivative of the second, that's going to be a little chain rule, plus the second times the derivative of the first, and that's going to be a little chain rule. So I'm going to put a little note next to this. You start with the product rule on this one. All right, so y prime equals first function x plus 1 cubed times the derivative of the second function. So I'm going to pull that 4 out to the front. I'm going to bring down my x squared minus 5. I'm going to drop my power down to a 3. But then I want to take the derivative of the inner function. So that's where the chain rule comes in. So the derivative of the inside part would be 2x. So that is first times the derivative of the second plus second, so that's x squared minus 5 to the fourth, times the derivative of the first, which is a little chain rule. So I start with my power. So my 3 comes out to the front, times x plus 1, my power drops down to a 2. And then I have an inner function on this one as well. So the derivative of x plus 1 is 1. So I'm just going to clean this up a little bit. So 4 times 2x is 8x times x plus 1 cubed times x squared minus 5 cubed. And then for my second expression, 1 times 3 is 3 times x squared minus 5 to the fourth times x plus 1 squared. We will stop right there, but I just will give you a heads up that later on in our course, we will have a reason to want to factor this answer. So you can see that there are common binomial expressions, that x squared minus 5 is common, that x plus 1 is common. For right now, you're fine leaving it exactly as it is. Okay. Our next example, and this is the last example we're going to do for this video, is a quotient rule problem. Now we see a little chain rule down here. I have a function within another function, but the bigger picture is that there is a quotient rule happening here. So I am going to start with my quotient rule. So low is my 4 minus 5x to the fourth. D high, derivative of 8x is 8, minus high, there's my 8x, D low, and that's where my chain rule comes in. So I'm going to start with my power rule first. So the 4 comes to the front, the 4 minus 5x carries down, and the power is going to drop down to 3. And then I am going to multiply by the derivative of the inside part. So the derivative of 4 minus 5x is negative 5. And that is all over my denominator squared. Okay, so we're just going to clean this up a little bit. So on top, I'm just going to pull this 8 out to the front. So 8 times 4 minus 5x to the fourth. And then here we've got a negative times a negative, so that's actually going to become a positive. 4 times 5 is 20 times 8. Well, actually, I'm going to keep the 8x separate. So I'm just going to grab the 4 and the 5. So I have 20. Now, well, actually, I think your book will combine all of those coefficients. So 20 times your 8 will give you 160x times 4 minus 5x cubed. In the denominator, all we're going to do is raise this power to a power. So we have 4 minus 5x to the 8th power. And you are done right there. But just in anticipation of what's coming up soon in chapter 4, if we needed to simplify this further, they both have a 4 minus 5x, which can factor out to the front and reduce with the denominator. Okay, thank you so much for listening. This is the first portion of your chain rule video. There is another chain rule video following this one with some other applications of the chain rule. Thank you so much. Good luck to you.